In this two-part series of videos, I will be presenting on a higher order Fox-Milnor theorem. In this first video, I'm going to go through the definitions of the Alexander module and the higher order Alexander modules, which are a natural way to generalize the notion of the Alexander module. These will be modules over non-commutative rings, and understanding these are essential to understanding what we'll talk about in the second video, which is a presentation of the main result and the ideas that go behind the proof. So to start off, I want to define the classical Alexander module. So to do this, given some knot and three sphere, I want to denote its complement by X, and I want to consider its universal abelian cover, which we'll call X naught. This is the regular cover of X with fundamental group, the commutator subgroup of the fundamental group of X. So its deck group is just the homology of the knot complement. The homology of a knot complement is always isomorphic to Z. So we sometimes call this covering space the infinite cyclic cover of X because we have this infinite cyclic action from the deck group. So here, and this will be true for any covering space, the deck group action will extend to a module action by the group ring of the deck group on the homology of the covering space. So here we have a module structure for H1 of X naught as a module over the ring Z H1 of X. Again, H1 of X is isomorphic to Z. So its group ring, we can identify, given some orientation of the knot, we can identify this with the integral Laurent polynomial ring. You can think about just taking the variable t to be, some choice of generator that, comes from the orientation of the knot, some choice of generator for the homology of X. So given this group with this module structure, what we have is the Alexander module. We'll denote this by A naught of K. This is a finitely presented module over ZTT inverse. It is a torsion module, meaning that for every element, there's a non-zero polynomial that will annihilate that element. And it has a square presentation. Given a square presentation, we can define the Alexander polynomial just to be the determinant of this presentation matrix. So a couple things to say about this is this determinant for a knot will never be zero. We can define similar things for links, in which case, for a lot of links, you will end up getting zero. But for knots, this will never be zero. The simplest you can get is 1 or a unit in the ring. And the second thing to note is that there is some indeterminacy here in computing this Alexander polynomial or in defining this Alexander polynomial. If we decide to take this to be the determinant of A, well, then we're going to have some variance in the Alexander polynomial we get depending on what presentation we choose. So here we account for this by using this equal sign with a dot on top of it. And in the context of this classical Alexander polynomial, this is going to mean that the polynomial is unique up to multiplication by unit in our ring CTT inverse. So given the Alexander polynomial, let's review what the Fox-Milnor theorem says. It tells us that if K is a slice knot, then its Alexander polynomial will factor almost symmetrically as F times F bar. So here, what that bar means is this is going to be an involution on our integral Laurent polynomial ring that is given just by inverting the element t. So we can think about this as f of t times f of t inverse, which is probably the way you're accustomed to saying it. So Fox and Milnor proved this for slice knots, but this holds more generally for 0.5 solvable knots. So what is a 0.5 solvable knot? Well, let's present the definition of what insolvability is in general. Is this very complicated definition. You're not really going to need to know the precise details of it to understand what comes in the next video. It just means that a knot K is insolvable if its zero surgery bounds a four manifold that we call the N solution which satisfies these three properties. So first, inclusion induces an isomorphism from the homology of the zero surgery to the homology of W. So this is going to give us that the homology of our in solution is Z, because the homology of the first homology of the zero surgery is also Z. Its second homology is very nice. It's a free abelian of even rank with a basis generated by smoothly embedded surfaces that interact with each other very nicely. And three, the fundamental groups of these surfaces under inclusion all lie in the nth derived subgroup of the fundamental group of our N solution. This is where the N comes from, an N solution. So the derived series for any group is just the series of commutator subgroups. So the zeroth derived group would just be the group itself. So if this N were 0, we would just have pi1 of W. If N were 1, we would have the commutator subgroup. If N were 2, we would have the commutator subgroup of the commutator subgroup, and so on and so forth. For half integer solvability, so remember the Fox-Milnor condition holds for 0.5 solvability. To get that, we just push the fundamental group of half of our surfaces. So take, for example, the SI, and we require them to be in the n+1 derived series. So again, you're not going to need to know this in full detail. We will make reference to, say, the first point explicitly in the next video. But everything else is sort of going to be absorbed in the theorems and tools that are used to prove the theorem. So we're not really going to have to focus on that too much in the next video. I just wanted to put this up here just for reference. This is what we mean when we say n-solvable or n.5 solvable. Okay, so now I want to define the higher order Alexander modules and their associated polynomials. To do this, to make things a little bit easier to talk about, a little bit easier to understand, I want to introduce the notion of twisted homology. So to get the twisted homology, I want to consider the universal cover of X tilde. And for the sake of brevity, I will denote by pi, it's the fundamental group of X. So again, like we saw before, in the fact that pi is the det group of the universal cover, the action of pi on X tilde extends to a Z pi action on the chain complex of the universal cover. So if I tensor on the left over Z pi with R, what I end up getting is what we call the twisted chain complex for X. So we denote this by C star of X with coefficients in R. So these are coefficients twisted in R. And if I take the homology of this chain complex, I get what we call the twisted homology of X with coefficients twisted in R. So we can use this notion of twistedness, this framework of twisted homology, to redefine the Alexander model. So in particular, the map from pi to H1 given from abelianizing, this gives us a right Z pi action on the group ring of H1 of X. And so we can just define the classical Alexander module to be the twisted homology of X with coefficients in ZTT inverse. So now let's define the higher order Alexander modules. And we're going to define these in a very similar way as before. And again, by considering quotients of pi by deeper elements of the derived series. So for the classical module, we were quotienting out by the first element of the derived series. Now let's quotient out by deeper elements. So I'm going to let gamma n denote this quotient. So gamma n will be the quotient of pi by the nth+1 derived subgroup of pi. And we would want to define, very naturally want to define the higher order modules or the nth order module to be the twisted homology module, twisted first homology module of X with coefficients in Z gamma n. Well, Z gamma n does not look like a polynomial ring. Neither did, Z H1 of X. But again, using an orientation for the knot or a choice of oriented meridian, we can actually make this look like a polynomial ring under some identification. So a choice of oriented meridian gives us a surjection from gamma n to the first homology of our knot complement, which again is isomorphic to Z. This identification with Z defines a splitting for gamma n, which gives us an identification of gamma n with the kernel of this surjective homomorphism, semi-direct product with Z. And this is a semi-direct product because, you know, when n is greater than or equal to 1 and gamma n is non-trivial, the group gamma n is not abelian, right? Because you're quotienting out by subgroups that are smaller than the commutator subgroup. And so you're, you know, going to get this non-abelianness in your group. The action from the semi-direct product is, well, given our choice of oriented meridian, in order to get your generator of Z to commute with the kernel of phi n, you have to act on the elements of phi n by conjugation by this oriented meridian. So that's the action that's going on here. Well, this identification of gamma n as a semi-direct product will extend to an identification of Z gamma n with this skew polynomial ring. So skew in this case just means that the variable and the coefficients are not going to commute. In fact, in order to, you know, rearrange the coefficients and the variables, you have to act by the same automorphism as you would in the semi-direct product, just extend it linearly over the group ring. So now we have an identification with a polynomial ring. So are we done? Can we, you know, define the Alexander module this way and extract an Alexander polynomial? Well, not quite. So for most of these group rings, we're not going to have UFD. So whatever this means in a non-commutative case, I don't really want to get into it. But we don't have a well-defined notion of factorization in these group rings. And so it's very, very difficult to extract an Alexander polynomial, much less a well-defined Alexander polynomial. Fortunately, our saving grace here is that these gamma n's are what we call polytorsion-free abelian groups, or PTFA for short. I'm not going to define what PTFA means. It's not too difficult to define it, but it's also not particularly important to define it. But a very important property of PTFA groups is that their group rings are what we call Ore domains. An Ore domain is essentially the non-commutative analog of an integral domain in commutative algebra. So in particular, we can localize every multiplicative subset that doesn't contain 0. And by extension, there exists a field of fractions, a skew field of fractions, into which both the ring and all of its localizations embed. So because what we have in Z gamma n is an Ore domain, we can define the ring Rn just by localizing the coefficient ring under the identification we saw on the previous slide. So what this does is it gives us a ring Rn, a variable nt, and coefficients in a skew field, which will be the field of fractions of the coefficient ring that we saw before. So whenever n is strictly greater than 1, this is going to be a skew field, so it's going to be non-commutative. When n is equal to 1, we actually do get an honest-to-God commutative field as our coefficient. Okay. These Rn's are PIDs, and they are also flat Z gamma n modules. So we can define the nth order Alexander module to be, first of all, just the twisted homology of X with coefficients in this Rn, but by flatness, this is going to be the same thing as the twisted homology in Z gamma n coefficients, tensored over Z gamma n with Rn. And I'm realizing now I made a mistake. So maybe you've noticed this Rn should be on the left, not the right. This is, you know, a typo due to several changes, edits I've made to this talk over the past week. So I apologize for that. This Rn should be on the left. Okay. So A and K, the nth order Alexander module, these are going to be finitely presented torsion R modules, Rn modules. And by work of Kohn, we actually have the same result that we would have in the commutative case for finitely generated torsion modules, or just modules over a PID. They decompose into a direct sum of cyclic modules. We had the same thing in this non-commutative case for Ore domains. our nth order Alexander module is going to decompose as this direct sum of cyclic Rn modules. This is nice because we can define the Alexander polynomial just to be the product of the generators of these ideals. Now, in general, if I have an arbitrary module over a PID that has this type of decomposition, the product of these generators I'm going to call the order of that module. I'm going to use this terminology quite a bit in the next video, so it's important to introduce that now, that this product we call the order. If the module is not torsion, well, we just take the order to be 0. And I mean, this tracks because you just mod out by the 0 ideal for the free part of your module. So that gives you a 0 in the product, so you get the order, it's just 0. Okay. So I'm using this equal sign with a dot on top of it again. And before, remember, we took this to mean unique up to multiplication by unit, which is definitely true here, right? If I change the generators by multiplying by a unit, I still get a module that's isomorphic to the original module, right? Because the ideals are exactly the same. But we also have the indeterminacy where if I rearrange the order of these cyclic modules, well, that's going to correspond to a reordering of the factors in this product. Well, I still get a module that's isomorphic to an of k, so I should still have an Alexander polynomial that is equivalent. So here we're going to take this equal sign with a dot on top of it to be unique up to multiplication by unit and reordering of the factors. When n is 0, and we're talking about the classical Alexander module, the classical Alexander polynomial, where our ring is commutative, reordering of the factors doesn't really matter, so that's just multiplication by unit. Algebraically, we can say this by saying that equal sign with the dot on top of it indicates uniqueness as an element of the following group. So we take the skew field of fractions of Rn. We want the multiplicative subgroup of that field of fractions. We want to abelianize that field of fractions, and then we're going to mod out by the image of the units of Rn. So if I'm unique as an element of this group, then that's the same thing as saying that it's unique up to multiplication by unit and unique up to the reordering of the factors. But you can just ignore this group if you want to and just take these words to mean what that equal sign with a dot on top of it actually means. So one thing to note is that if we define a0 of k in the way that we just defined the higher order modules, notice that we don't actually get the module that we defined earlier. What we get is something we call the rational Alexander module. So this is just the twisted homology module with coefficients and the rational around polynomial ring. And that's because if we follow, the same process, we invert the elements of the coefficient ring, which in the classical case is just z. So we get Q adjoint TT inverse. This changes very little for our purposes. This doesn't change anything at all because the Alexander polynomial looks very similar. The Fox-Milnor condition still holds. I don't really know if there's a case where you get that kind of factorization by moving to Q TT inverse. I'm very skeptical that you might get it there, but it's possible. But it doesn't really change anything from the perspective that we're trying to there's perspective that we have in this talk. You do lose some information in general from other aspects of the Alexander module, but not from anything that we really care about here. Okay. The last thing I want to talk about, and this is because we talk about this in the next video, we get into this in the next video, we can actually define these Alexander modules and these rings, for example, Rn, where we localize the group ring. We can do all of this algebra very similarly for an arbitrary topological space if instead of quotienting out by the derived series, we quotient out by something we call the rational derived series. So the rational derived series is very similar to the derived series, where it looks like this sequence of commutator subgroups, except we at each stage we multiply by this other group that we're calling Cn. And don't worry too much about the definition of the rational derived series. I'm not going to get into the details of it in the next video. But the one thing you should know is that when I quotient out by the rational derived series, I'm guaranteed to get a PTFA group. Like always will get a PTFA group. In fact, the rational derived series, so the nth rational derived subgroup, is the smallest subgroup of your group containing the nth derived subgroup, such that when I quotient by this group, I get a PTFA group. So that is, in words, what characterizes the rational derived series. It is the smallest group containing the nth derived subgroup, such that when I quotient by it, what I get is PTFA. And we really want PTFA groups. Well, one, for the reason of localizing. This localizing allows us to do a lot of algebra that is easier to do, which is always good to have something easy to do, or easier to do in the non-commutative perspective. But PTFA covers also have really nice properties. So these are regular covering spaces that correspond to PTFA subgroups. These are really nice covers topologically with a lot of nice algebraic properties on their homology. We're not going to get into any of that, but the reason we want to use PTFA groups is non-trivial in this context. So in the next talk, in the next video, I'm going to be talking about these Alexander modules of, say, the zero surgery of a knot, as well as the Alexander modules of the n solutions of a knot. And in this case, you're not guaranteed that quotienting out by the derived series is PTFA. But if you pass to the rational derived series, you are guaranteed PTFA. Okay. So that's all I want to say for this video. Hopefully, I'll see you in the next one, where we present the main result for this talk and the ideas behind the proof. So I'll see you there.